is. So our first lecture in the afternoon is going to be by Johan van de Koppel from the Royal Netherlands Institute for Sea Research. So yeah, thanks a lot, Johan, for being here, wherever you want.
You hear me? I think so, eh? Yeah, great. So thanks for the organizers to invite me here. I really like it. I'm an ecologist from background, and talking to physicists, particularly when I was young, plain scary. But at least in the past 10, 15 years, I noticed that actually, well, I can understand. As long as it's not special or general relativity or quantum physics or string theory, I can manage. So I've been interacting with physicists a lot, and I love it, particularly because the focus that they have on the principles and on simple models and so on. And so yeah, I'm going to talk a little bit about basically the ecosystem, an ecologist's view on pattern formation. That will be actually, I will start with that tomorrow. Today I will keep it more basic, and well, hopefully learn you a little bit about the nice things that you can find in ecosystems with regard to pattern formation. So first, a little bit about myself. I am from the Netherlands. I should have made a picture. I mean, if you ask me to tell you about every country in South America, I would be like, I don't know. So I don't expect you to know precisely what it's to the east of England. I think you know England. And so within that, I am in a marine institute. So not at university. They always put marine institute in the middle of nowhere along the coast. So in a small little village with a huge church and very religious people. And this is the institute. It's very nice because we're right next to the sea. So I actually see the tides going up and down, and you see the whole ecosystem developing in front of you, which is great. We actually study things like this. This is a salt marsh. It's a very small one. That's because I'm standing on the dike. Well, we are below sea level, so there's a dike separating us with the water. And there's a little bit of nature left before you go into the deep and the ships, is this little salt marsh. And you can see how patchy it is. And actually, I will talk today about the processes that make this thing patchy and how this works. So we do that in all sorts of ways. I'm going to go very quickly over it. So we use remote sensing techniques to study how this salt marsh is eroding on the edge. You can see the red band there, which is a retreating salt marsh. At the same time, in front of it, it's expanding. So it's a sort of a mixture of eroding processes and expanding vegetation at the same time, which is a very interesting phenomenon that I have spent some time on. We do all sorts of measurements. Actually, I must say I don't do that myself so much. I used to do it more when I was younger, but nowadays I ask my students to do it, PhD students to do this. And we do all sorts of things like measuring how wave action is buffered by the vegetation and what the value of these ecosystems is. Of course, myself, I am more of a modeler. So I study how the interplay between organisms and the physical world creates all sorts of dynamics in ecosystems. This cliff, as you can see here, the eroding edge of a salt marsh that retreats has to do with wave action and the steepness of the landscape. I'm not going to talk too much about that, but mussel beds I'm going to talk about, the patterns thing there. And this is an aerial photograph. I will come to that later. And then, of course, we make models. And these models look all the same. That's because any model that has sort of Turing-type pattern formation comes down to the same principle. So you get the same sort of patterns that you also saw in the talk by Erwin. I will talk about that tomorrow, and also about the underlying processes and the generalities that you can find in these sorts of ecosystems. So myself, I sort of moved on to more complex things. This is a picture of a salt marsh where we are modeling actually how a simple, very small-scale interaction can scale up, repeat itself at different scales to make a very complex, large-scale landscape like the creeks network that you see here. It's just a simple, single-scale interaction that causes this by sort of repeating itself. And I'm now working on it actually also with Nigel. We are contributing actually very nice perspective. I don't think that we will talk much about that, but we're using some thermodynamics to understand how this forms. This is more of a scientific part of my talk. Of course, these days, particularly in the Netherlands, I mean, if you're a fundamental scientist, you're a loser. And so, how irrelevant could you be? And so, everybody has to help. We have to talk to the manager and talk to the guy who owns the harbor, and I talk to this and I talk to that. And I was talking to nobody. And so, you could see the problem that I was in. I solved it in my own way. I'm going to talk to you a little bit about that in my last lecture. Is I start to make pretty pictures. So everything you see here is virtual reality. And the reason for that is that nowadays we talk about these self-organizing ecosystems and the beautiful, highly structured off-equilibrium landscapes. Well, where do you find them? Well, in hugely odd places and so on. But that was not the case many thousands of years ago. Then our own lands, the Netherlands at least, it was highly self-organized. All the streams, the salt marshes, all these ecosystems, peatlands, hugely self-organized. And I sort of depict these all former landscape and try to convince people the value of nature that comes out of that. So that actually my sort of iconic explanation is like, well, let's go out in nature. And they picture themselves walking into a field with cows. And then I'm thinking like, no, that's not nature. Nature used to look very different. And that I try to combine. And this is sort of accepted as an sort of application, so I don't have to talk to managers. That's great. Okay, get back to my lectures. So today, actually, I will start explaining basically how you make a model of an ecological system. I'm actually not sure how much you know already about it. I will ask some questions during the lectures, like, do you know this, do you know that? So it will be basic ecological theory. And tomorrow, I will start talking about pattern formation in ecosystems, basically what's called the Turing patterns. Wednesday, I will move on to modeling pattern formation with individual organisms as a step towards a different paradigm of modeling, and also driven by very much the movement of organisms. And that type of pattern formation, driven by movement, results in something very different than what you see in the Tuesday lecture. And on Thursday, I want to talk a little bit about the last stuff that I showed. It's my current ongoing research on these hydrodynamic systems and how patterns can develop in these sorts of things. So, a bit about my ways of teaching. I, of course, like to focus on principles, like we all do here, obviously. If you show a lot of equations to ecologists, they typically do two things. They fall asleep or start to look at their telephone. So I try to minimize that. So not too many equations, lots of photos. And I also like historic context, like how did it look in the old days? But also, how did theory develop during, in the past 200 years? So I present a lot of pictures, like this one. This is a nice one. Pieter van Breugel from Belgium made this nice drawing and etching. How do you say that in English? Actually, well, whatever, sort of a painting. And of how in these days they saw how the world, the natural world, was interacting with itself. Like you have the big fish, and they eat the smaller fish, and the smaller fish eat even smaller fish, and the humans also eat fish that are eating fish. It was actually at that moment a remarkable thing to mention, that everything was eating itself, like an ecosystem with a food web in it. Exactly. So exactly, I'm a bit puzzled by the fish-eating mussels that you. Oh yeah, there we go. The fish-eating mussels here. That's the interesting thing. I've never seen a mussel eating fish, but that's the perception that they had in these days, I think. And so a very nice mentioning is there, that particularly by the English biologist Thomas Henry Huxley, who said basically that, well, at that stage they didn't have the idea that humans could affect the balance of nature much. We were just a small little thing that really didn't really affect how nature was working, so we couldn't really affect it any bad way either. We didn't have much of an effect. Well, in the past hundreds of years, we have seen that presumption is not true, and that has driven, of course, a lot of modeling on ecosystem, well, the interactions that are shaping nature. And so today's topic will be about that, and I want to talk about a couple of types of ecological interactions. I will start with predator-prey interactions, so predation and predator-prey cycles as a phenomena. It was briefly touched upon by Veronique. If I get to it, maybe I will, maybe I won't. I will talk about competition, which is also a very classic form of ecological interactions. And then something which is actually quite new is how do you then interact if you do not eat each other, but if you influence each other in a different way by modifying a chemical or physical property of the environment. There's actually not that much theory on it. I find it still remarkable. If you can make very simple models that show some principal differences between how an interaction can change when you do not eat each other or compete with each other, but when you modify each other's environment. And I will talk about that at the end, I hope. I have a question, actually. So if I would talk about Lotka-Volterra Lotka-Volterra predator-prey models, who here knows what that is? Well, lots of people. So if I would say I would use phase plane analysis and or phase space analysis with isoclines to analyze a system of two ordinary differential equations, who knows here what I'm talking about? Also everybody. Okay, thank you. I will get to the end, don't worry. And so, okay. To come back to this idea of how does nature work. Imagine yourself in a world where people think that actually there's just a balance in nature, things change a little bit, humans don't really affect that. And so in that world, there was a little problem happening, which was studied by Vito Volterra, is, well, this classic figure of the catch in the Adriatic Sea, which was the inspiration for the first predator-prey work occurring in, at least in Europe, was the puzzle of the predator catches in the Adriatic Sea, which went up from 2004 to 2018, and after that it collapsed suddenly, which was considered a problem. I must say, I think like, well, they didn't fish much between 2014 and 2018. After that, they started fishing again after the war. So I'm not so sure what's the problem, but at least at that stage they thought it was a problem. And well, who do you ask then? Would you ask a fisheries biologist? Nah. Do you ask an ecologist? No. In these days, the only people studying, but the only thing that ecology studied was chasing butterflies with a net and looking at plants. And so they asked a physicist. It still hurts a little bit, you know. And so they asked a physicist. And this physicist, well, what did they do? He made a very simple model. And this is far, far before computers. So he made a model of a predator-prey system. And of course, in a simple way, because you had to do it all in, I'm going ahead of myself. This was Europe, a problem in Europe. And at the same time, there were reports from the United States, which had another puzzle, which turns out to be a very comparable one, which is this, this well-known picture of the cycles of the snowshoe hare and the lynx. And of course, in these days, they didn't know about population cycles by measuring populations. They didn't measure any populations, but they did measure how much furs came in at the Hudson Bay Company, as you can see here, as an example of a fur trading company. And they saw that these furs, I guess it must be the lynx, were going up and down all the whole time without having a good explanation for it. So this was an inspiration for the American part of the story to make a model for this. And they started independently making a model to analyze this. And they came up with the predator-prey, Lotka-Volterra predator-prey model, which you see principally here. I mean, principally in terms of that, I don't specify the model immediately. I just look at the general structure where the components are given as functions. And for instance, you have a function describing prey growth. And you have a function describing predation. And you have a function describing predator growth, or what is consumed by the predator of the prey is then determines the growth of the predator. And you have a mortality term for the predator, because otherwise the predator would go into an infinite size. So you have a very simple structure that forms the basis of the predator-prey model. And just to give you, these different functions have names. It's good to mention that. It's the prey growth is often used as the logistic growth equation. For consumption, they typically call this a C function. They call this the functional response. And growth, they call this the numerical response. And they are highly related. I will come back to that later. So what model did they come up with? Let me have a look before I go ahead of myself again. Oh yeah, as I said, this is the functional response and the numerical response. I've already described that. So they are functions that are determined by the density of the food. So both C and G are a function of food density, and they're multiplied by, so they basically tell you how much food is being consumed per predator. So if you then look at these models, they look like this. So this is the model that I think both guys made independently, although I do not know every detail there, but it was a very simplistic model, linear. Of course, physicists like that very much. Linear models are great, but don't forget, in these days, they didn't have any computers. If they wanted to model the dynamics, that means going on paper and computing every little step in the model that you made if you want to make a simulation. And so that was not a favored activity. They would rather analyze the model with mathematical techniques or graphical techniques. And so a very simple model where you just say like, well, there is a linear growth term, as you can see here, and there's a term which is the functional response, which just says like, well, the predator and the prey are just roaming around through the ecosystem randomly, and they accidentally bump into each other, and then the predator eats the prey with a certain chance, which is called A. And basically, you're presuming there that they're nothing different than molecules roaming around and interacting and reacting to each other. Then this E times N times P function you can find back here also. But it's multiplied by the term E, which basically means, well, if you, also for you, if you eat 1 kilogram of food, you don't grow 1 kilogram, luckily. And so there's a certain conversion efficiency in there. And that E is typically we use 0.10%, which is for humans pretty huge, but for shellfish, for instance, actually it's 0.2 to 0.3. Is the conversion of what from the biomass of what you eat to your own standing biomass as an individual or as a population. And there's a mortality term M. And so if you want to analyze this model, and I'm going to switch for a change to the where did the charts go? I can take them here. Okay, find them. Thank you. So to analyze this, I think this is a classic. You probably all know it, but let's just repeat it and know what it's all about. So you have a space that has the predator and the prey, meaning every state of the system is a point in this field. Here, low prey, low predator. Here, high prey, high predator. So every configuration is a certain point here. So you can follow the state of the system by moving through this space, which is, of course, is a nice thing to do. And so, of course, you can sort of dissect space in areas that have different properties. So one of the properties you can study is like, do my population increase or does it decrease? And so you have to put a boundary in there. And the boundary is an isocline, like isoclines in mountains. It delineates a certain elevation. Here it delineates a zero growth configuration. And so if we want to do that, we have to look at the equations. And I'm going to take the one for the predator first. That's the one that's easiest. So we look at the predator differential equation. Is E times A times N times P minus M times P. So if we want to get an isocline, if I start boring you, just fall asleep. Anyway, then you have to put this to 0. There's no change. And you can reduce this nice linear system. You can reduce it incredibly because you can already see the P drops out. Basically, it doesn't matter for the predator how many predators there. Can be huge amounts of predator. It's only the prey density that determines how much prey is, how much the predator population grows. So N equals M divided by E times A, which is a constant, N constant, whatever, or N star, or whatever you want to label that. And so basically we can say like, well, there's a certain value here, let's use a color, at which the, no, looks white mostly. Okay, well, yeah, whatever. Where the predator has a zero growth. So it's good to look at this and see what this means. And you can actually draw arrows to look for which direction the system would change if you look at the predator. So what happens here? And before you give me an answer, you have to think logically. Here, at this density of food, the prey population is just in equilibrium. What happens if you give them less food? They go down. Yay, not so difficult. That way. Actually, I'm going to do it a little different. Okay. And what happens here? Lots of food, like us at lunch. Population increases. Yes. And then we can do the same for the prey. So dn dt equals r times n times a times n times b. We can put this to 0. We can remove the n from the equation, and we end up with b equals a divided by r. So again, a constant. Basically meaning, for the prey, it's only important how many predators are there. The competition does not play a role in this model. And so that's a p-value, so a straight line. So this determines how well the prey population can grow, given a certain amount of predator around. Well, what happens on the top side here? Huge amounts of predators around. So what happens to the prey? It goes down, yes. So that means this direction and this direction. And so, and here, not so many predators around. So what happens on this side? It goes up. So you can already see the general directions of movement by looking at these arrows. You can see, well, it sort of goes round, isn't it? Yeah, well, how does this work? Of course, well, I'm an ecologist, so you do all sorts of complicated math. I refer to my mathematical colleagues for that, or physical colleagues for that.
Pointing out that n equals 0 and p equals 0 is also a null sign.
Equilibrium, yes. Yeah, good point. Thank you. Thank you. It's good to know that there's somebody checking on my lectures here. So, of course, at the intersection point, both are in equilibrium. So you have an equilibrium here. And here, both are 0. It's also an equilibrium. Are there any more equilibria here? That one. Oh no. Here. Huge amount of prey and huge amount of predator. No. So here basically means if you don't have any prey, don't have any predator, nothing happens. It's logical. You have no system basically. So if you would look, for instance, if you had a system with lots of predators, no prey, what will happen to the predators? They will just die. So, and what happens to if you? Well, actually, there's no other. I think I made a mistake in thinking. But so if you have no prey, then there's only one point which the predator will just explode. Of course. Sorry, I'm making a mistake myself here. Anyway, okay. So what will happen here? Anybody have an idea? I made a nice simulation. And we'll have the same trick. We'll do the same trick the whole day. I'll show you the model, and you tell me what happens. And I will say like option this, option that, and you have to raise your finger. You're not allowed not to raise your finger. You have to raise your finger for one or the other. So what will happen here? Will it go to the equilibrium in the middle? Nobody raises. Will it go someplace else? Nobody. Will it start to cycle? Yes, you already know the answer, so yeah, of course. So with Lotka-Volterra model, this is the answer. SI cycle. What is striking about this model, you have a sort of starting condition, and at night it starts to oscillate. If you take a different starting condition, it also starts to oscillate with a bigger cycle. So it always cycles. It's a very robust cycle. So like in any situation, cycles. So you can see the physicists be very happy. We've solved the problem. In any case, it will always be cycles. It's amazing that the rest of the world doesn't cycle. And so what do you think how the ecologists thought of this when they saw this model? In the ecological world, it was like, what? predator-prey system with 2 equations and all this simplicity, and you think that this is any reflection of the real world? That was, well, in this time, ecologists were focused on details. We're focused on like, first of all, the names of all the species, and how did they interact, and how do they fit together? Actually, not interact, how do they co-occur, and all these sorts. Very descriptive. Focus on the details, focus on all the factors that are shaping nature. And he comes a physicist, and he comes with a ridiculously simple model that explains everything from the viewpoint of cycles. And so that was not accepted as a realistic model. So let's make this model more realistic. We are physicists here. We can do that. We can make this model a bit more realistic. And so let's start with this beginning. And for that we need, who knows what the first thing to add here and what field it comes from? Who knows? It needs an economist. Any idea? Malthus? So this idea that the predator will just without predators, the prey will just exponentially grow and go to infinity, fill the whole Earth. You have heard many times that within a few decades, the whole Earth will be populated with just one species if there's exponential growth. The classic explanation. And of course, Malthus, being an economist interested in use of capital and all sorts and how equilibria are shaped by economic processes, started to use that idea on populations, human populations. And he basically said, like, well, population cannot grow indefinitely, but they become limited by the resources. The poor people will starve, and they will rebel, and they will destroy the whole society. So we have to prevent this from happening. That was his take on it. And this, of course, he made a whole complicated theory around it. I must say I didn't really read the book very much, a little bit. But basically, this was the basic framework from which we worked on in the prey model. And later on, a Belgian mathematician says, like, well, starting from the ideas of Malthus, you have to sort of change this into a population that actually the growth rate drops, and then it reaches a maximum. So you can already understand, of course, that here we have this term here. You have R times n, which is just exponential growth. You multiply this with a term here, which is 1 minus n divided by k, which starts to reduce the growth rate from R to a value of 0 when n is equal to k, because then the term here becomes 0. I think you have heard this many times before. And, well, of course, you can add this to the equation. As you can see here, logistic growth equation inserted into the model. And, well, what will happen? So, first of all, one possibility, nothing changes. Is that true? No. Okay, so other possibility, it will just go to the equilibrium, at the equilibrium point there. Is it? Who thinks this? Or what will it do? Well, let's just have a look. So we see that the oscillator behavior with this configuration is not lost, but rather it sort of diminishes slowly by the dampening effect of the logistic growth equation, and it finds itself a stable equilibrium at the intersection point. So this was one step ahead. The only problem with this model is there's actually, with this model, no configuration that actually gives you patterns. So we made the model more realistic, and it does worse. This doesn't really help. So yeah, realism doesn't always help with getting better models. That's one lesson you can take from it. But of course, people started to build further on because, of course, I mean, prey populations are limited by their own resources. So it's just a bit silly to ignore it also. So there must be more going on. And for that, people started to look at the functional responses and the numerical response, so to say. So the rate at which the predator was eating the prey. And the assumption earlier on was that it basically just was a purely random process, like gas molecules accidentally bumping into each other, reacting, which was a bit silly. And of course, you can make this hugely complicated. You can actually make the predator chase after the prey and all sorts of things. But the first thing they thought, like, well, these cycles are sort of population explosions and by the prey, and then the predator just eating them away like mad. And collapsing the prey population. Maybe the predators can't eat so fast. Maybe they just are, sometimes they're saturated. And so they changed this CN into something that is not a linear response, but that's the work of Bas Holling within ecology. Made this what's called the Holling-2 functional response within ecology, or the Michaelis-Menten response within physics, chemistry, or the Monod equation within other fields, or the Hill equation. So there's so many forms where this equation has been labeled and linked to specific people that the equation has like a dozen names, I think. So it's actually a very general thing popping up in various fields in ecology, but the basic idea behind this is that there's a maximum rate at which you can eat stuff. And the prey population, oh sorry, went too fast, wrong button, is increasing. The consumption rate is increasing with the prey population, but levels off to a maximum, which is given by the term A here. And B in this term is basically, sorry, A is the maximum, as you can see here, and B is the value at which this curve is at half maximum. So it's a very simple curve, very simple equation. It's also very solvable. You can easily manipulate it, so it was used a lot. You can just as easily use an exponential equation or something like that, or different versions. And but this one is actually the easiest, the most convenient to use. And there's other forms of it. Holling came with a whole series of, there's Holling 1, Holling 2, Holling 3. There's actually some people call it Holling 4, although I don't think that Holling actually made that. So that Holling 2 is puts a quadratic term on the N and the B, give you a little dip on this side, which was linked to predator switching behavior. That means that at very low resource density, the predator would not eat the prey so much anymore, because it switched to different food, and therefore giving a sort of a safe zone for at very low densities for the resource. But let's go back to the former one, which is this one. So what does it do when you put this into the Lotka-Volterra model? Well, it starts to look like this, of course. You replace the linear term with here the Holling-2 functional response, equally in this part, multiplied by E, which is the conversion efficiency, and you get a model that basically starts to look like this. So now the isocline for the prey, I didn't explain how the isocline changed. The isocline in the former one changes by just basically dropping down, meaning that the equilibrium value for the prey drops down when the predator density increases. Now it becomes a bit more complicated. It becomes a sort of a parabola with the maximum. And you can also investigate here what would happen. So if you look at this model at low density, you would say like, well, so this is the carrying capacity for the prey is pretty low here. So it doesn't, it's not a very productive prey. And so what you get is just goes to the equilibrium again. So this doesn't help. We want to have a even more realistic model, hopefully getting the cycles back again. And this is what we get. It still goes to equilibrium. It doesn't help much. But so what happens if you increase the carrying capacity? Well, then suddenly if you do it with this configuration, you see that the cycles are actually back, but not completely. They sort of still go to an equilibrium, so not an everlasting cycle, it's a dampened cycle. But the bigger you make the carrying capacity, the longer it takes for the system to reach that oscillation. So that simply, basically because you have a prey population which is more potential grower, so when there's a collapse of the predator population, the prey population can basically explode and takes a little while for the predator to catch it up again. It becomes interesting. You can see, of course, this is a parabola, this curve here. And it has a maximum. Of course, now it becomes very exciting what happens if you go beyond this maximum. And that's, of course, very interesting. You can see that here. And and actually, it goes to what's called a limit cycle. This system is actually, I should also have a simulation in the middle where actually if you put starting point just outside of, directly close to the equilibrium, but just a little off it, you will see it spiraling outwards. So this oscillation is a sort of an attractor, a strange attractor that can involve. It's a simple strange attractor, but an attractor that is a dynamic, has a dynamic shape. So a limit cycle. And so this was actually, in these days, a big deal. And in these days, ecologists still had more belief in mathematical and physical approaches. Now it's less. So, but this was at the moment a paper in, as you can see here, in American Naturalist, and in the end, in Science, because it came to an interesting prediction that with an increase of productivity, you have a system becoming less and less and less stable. And that's actually a remarkable result to have. Although it was also criticized, because where do we find these population cycles? Well, typically you find them hare lynx, which is in Canada, or at least in the cold areas of the Earth. You have the what is it, in Finland? You've also the I cannot remember the animals involved. Little mice that are also cycling, also show cycling behavior. That's actually where we find this cyclic behavior. We don't find it here in Brazil, at least not that I know of. Maybe you know better, but I have not heard about cyclic population cycles in Brazil, where there's actually a huge amount of... Okay, interesting. Would that be an...
So eutrophication of lakes
creates cycles.
creates cycles. So the more nutrients you give, then you can have these algae blooms. Yeah. So suddenly you can't swim, you can't drink the water, everything goes dead.
Yeah.
And,
okay.
and you can get extinction because they can be, these amplitudes can be very big.
Okay.
But it's a marine
I think you need to tell me
context.
about this. You need to send me the reference to this this work. It would be interesting to integrate it in this study. And so the funny thing is that the empirical examples are actually for, well, I used to say that at least, from low productive systems. Okay, any questions so far? I just race on, and I...
Thank you. When you say the empirical examples from the low productive systems, you mean that violates the assumptions of the model?
Yeah, I would think so. Yes.
Yeah.
Yes, you will. Actually, you would. And of course, I have some time left. I think I can spend some more time. I will. I had thought to add something, and then I removed it again because I think it took too much time. But I will unhide it. Unhide. And so, actually, there's interesting work coming out of that. Okay. So people actually were building on further on this, and of course, what would be a limiting? What are we missing if we basically transport this idea from the cold regions of the Earth, Finland and Canada, towards the tropics, and say this ecological interaction becomes unstable? What are we forgetting?
Multiple species?
Yes. That's absolutely right, but can you be a bit more specific?
Like if you can switch your food and you live in like seasonal environments, maybe your resources are constantly...
Would be very interesting. I'm actually wondering whether right now somebody should have tested for that. But so, in principle, you're right. It's the systems are too simple. And what people did as a first step was not to make a competing system with biodiversity, with alternative food sources, but they said like, well, let's just put a predator on top of it. Put a top predator on top of it. And that was done by, well, actually many people, but one of them is Alan Hastings. And he was interested in what sort of dynamics comes out of it then. And so he basically just repeated the model by putting a top predator Z. Now he has a model X, Y, Z. You can see X is just the prey in the same way if I described it in the previous model. Then there is the middle predator, which is the little shrimp in his model, in his thinking, is has the holding two function response and numerical response, and then is eaten itself by a top predator, which is Z. And that led to very interesting results. First of all, if you do that in a simulation, then this is what you get. So you can see here, blue is the prey population. This is just a simulation that I made. So if you release a predator in this system, then you see that that's the red line. That at first collapses, but then catches on by eating lots of food, and you get an oscillation. But after that, the top predator comes in, because it has enough of the predator P. And you can see the invasion of the top predator, the green line, is slowly removing the oscillations in the predator-prey system. So a top predator can actually dampen a predator-prey oscillation, leading back to a stable system. Of course, you can also wonder, well, we were having a trick of increasing the carrying capacity. What happens actually if you then do that further again? So we make it even more productive. Well, then you get a very nice, that was actually a nice paper by Alan Hastings. You get very strange population cycles. You get cycles within cycles, and you see this. This is what's called the upside-down cup attractor. I think it's a movie, actually. Let me have a look. Yeah. So it's a 3D structure where basically on the bottom you have consumer and resource, and it oscillates. And that leads to the buildup of the predator, which is on the z-axis, dampening the first oscillation. And then the predator collapses back, and you get a repetition of the whole process. And so you get, if you just pump up the volume even more, you get these oscillations back again. So it's a fight between maybe an more extended ecosystem and increased productivity. And this is called the upside-down cup attractor, because according to Alan Hastings, this is basically a model which is very, very similar to the original model by, what's the name of this? Lawrence, exactly, thank you. Lawrence and his butterfly attractor. It's a different system, but it's just reconfigured his model to be a predator-prey model, a predator-prey top predator model. And in this way, showed that predators' prey systems are also similarly vulnerable to the chaotic dynamics. Basically meaning that although it follows this basic shape, because of the chaotic nature of the system, you never know precisely where it will be. A little change in the parameters or a little change in the starting conditions, and we will follow a different trajectory. The predictive nature of this system disappears as time is progressing from the starting point. So just a little extension of the previous work. Any questions so far? Okay. Then summarizing. So we discussed, well, predator-prey cycles.
There is a question here.
Oh, sorry.
Yeah, I mean, these parameters that you have in the model, the growth rates, the competition rates, etc., in a real ecological setting, they are not really constants. They may depend on location, they may vary over time, and all of these things. Is that considered in population dynamics? Not the noise from the demographics, but the noise from the spatial variation.
Just as a standard sensitivity analysis, this.
Yeah.
And that's actually not the most interesting thing, actually. It's more like interesting is how accurate can you actually measure these things? Mm-hmm. And then how predictable are they really? So then the whole storyline, there was actually quite a discussion within the field of ecology, that there were people that were pointing at the importance of chaotic dynamics to allow species to coexist with each other in any ecological system. And they actually gave nice examples of that in a model context. But aquatic ecologists, there was an aquatic system that they modeled, and aquatic ecologists, they were strongly disagreeing and didn't follow this line. And so it was quite a discussion with the whole argument like you're just looking at noise. And actually, the nice thing was, there was from the University of Amsterdam who studied together with a person from Germany. It was a person from Germany who scooped out a container of water from the Baltic Sea and followed that for 3 years or something. Just every day, taking a sample, measuring all the little animals, of course, mostly the microbial and and zooplankton in the water, and followed it for 3 years without doing anything with it. And then he brought this to the guy in Amsterdam, and he was like, wow! And then they basically showed that under very much fixed conditions, with a fixed set of parameters, you had perfect chaotic dynamics under completely constant conditions. And that was, I think, a very nice example, and that really closed the discussion with whether actually chaotic dynamics would exist in ecosystems. They do. Yeah. Okay, yeah, so we discussed, I guess, well, I would say that this is like...
Sorry, Johan, there is one more.
Oh, sorry.
What's the effect of discretization on these models? Like finite populations, discrete individuals?
Oh, you get much more... Sorry? I get the answer here that it will be discussed tomorrow. I'll just give a little bit of my own answer. Will be probably be he will put much more attention to it. Is that if you have this, the discretization will destabilize a system which could be stable if you would have an infinitely small time step. So chaotic dynamics, the classic logistic map, can basically be derived by assuming a population with a certain step size, creating that sort of chaotic dynamics. And that would then, at that moment, be driven by the step size of the model or by the population step of the reproduction cycle of the organism involved. That was, of course, the argument of, I think it was May again that made that paper. I hope I'm not giving away all of your lectures. I guess not. So, no. Great. Yes.
Could you just go back to the upside down cup, please? Because I'm not sure if I understood exactly what you mean by a chaotic trajectory. Like, because if whatever you do in that graph, by the end of the day, you're going to have a upside down cup. So what do you exactly mean by a chaotic trajectory?
Actually, it's good that you continue on this. So basically it means that if you would put your dot, like where it is now, the black dot there, it will follow generally the dynamics that you see here and change in a way that you would expect. If you would put it one line up, at first it would follow almost the same trajectory, but as time progresses, the difference between the one trajectory, simulated trajectory, and the other simulated trajectory will slowly start to deviate to a larger and larger extent. Well, at some point, after some large amount of time steps, they're completely not the same anymore. So while in one simulation it was going up, the other simulation was going down. So you can't predict anymore what will happen, say, in 100. You can predict what happens in 10 time steps, but you cannot predict anymore what happens in 100 time steps. And that's the essential behavior. But your point, it's still an upside down cup. So that actually is very important. It's a very important thing. Chaos exists in ecosystems, but it's still within a bounded structure. And I translate it like this. I mean, basically it comes down to, under certain conditions, in Brazil, if you take out humans, it will be a forest. You won't know what forest, but you're sure it will be a forest. And so that's sort of the way that you have to deal with that. And of course, any manager that you talk to will say like, no, I want to know from you exactly what species will be growing here in 30 years. And they have to say like, well, I don't know. But I know it will be a forest. And so that's not very pleasing the politician, but that's actually the interesting interactions that scientists and politicians can have with regard to understanding the basic nature of an ecological system. It is not always very predictable. It's like the weather. Any further questions? So repeating, I think you know basically the lessons that you get here also from this. I think most of you have already heard a lot of it. So predator-prey cycles and use of functional numerical responses as a different way to shape the interaction between the predator and the prey and how that affects the dynamics of an ecosystem. And so the different types, and of course the phase space analysis and isoclines that you already knew. And of course the stability properties are also important in this context. Normally I would do that already in an earlier lecture. I sort of skipped over the stability part. I should have talked about it a little bit more. But maybe it's also interesting, this is what an ecologist gets to learn. This is the classic interaction lecture for an ecologist. So you know what to expect if you talk to a mathematically oriented biologist. Okay, well, I would like to make the next step is competition. Of course, I start with a question again. What sort of competitions are there? Give me some fingers and give me some labels and names. Anybody? Guys are too modest. Yes, thank you. A competition for space. Well, oxygen, a resource. Competition for space and oxygen. So, light is a very nice one because it's so non-linear. It dampens. It's not different species experience different lights and influence each other differently where they are in the light gradient. The light is complicated. A resource competition is oxygen. You lower the oxygen concentration. Both are experiencing the same oxygen concentration. A resource competition. Space is an interesting one. What is space? How can you compete for space? Does spatial competition exist? Or what are they competing for? Do you know any organism that is competing for space? Sorry? Humans. We're not competing for space. Well, if we want to have a house, and a lot, maybe we are. Okay, but any tree, the next tree can just grow next to it. It's not competing for space, it's competing for the resources, light and nutrients.
So micro-environments maybe, like little, like you asked about space, right? So
yeah.
Space could be the form of dens or something which is a little bit higher or like specialized space.
Yeah, but is it then space?
Yeah.
So I find space intriguing. So I definitely, competing for space is a concept in mathematical biology. But what it actually is, I always find very
ecology
intriguing.
as well, right?
Sorry?
It's also in ecology.
Yeah, sure.
Yeah.
But that doesn't mean that I agree with it. Come on. And then look at this picture. Let's look at that picture there. This is the classic picture of competition. Like we have a drop of water, and man, there are like hundreds of species of algae in it. How can there be so many species of algae in this water? How can we explain this? How can we look at how the interactions between some drops of some ecosystems have just one plant, particularly if it's light competition involved, and then the drops of water can have hundreds of species in there. It's a classic problem, but it's also very old. This is a much newer one. Have you got any idea what you see here? This is my world. You see, actually, I think it's Saliconia. No, it's not seagrass. Seagrass won't stand up. Saliconia, a small little plant. And it's a small little plant there sits on little hills. And then in the depressions, what you actually see are little heaps of lugworms. Lugworms are growing there in the sand, and they make little heaps. And so what do they compete for? You might think that you might think they're not competing because the Saliconia is standing on the hilltops, and the Arnicula, the lugworms, are sitting in the depressions. They're not competing at all, is it? But who makes the little hills? It's Saliconia makes the little hills. It stimulates sedimentation, moving it up. The lugworm does exactly the opposite. It mixes the sediment continuously, so it goes down. So they are competing. You might think they are competing for space, but no, they're modifying the environment. It's competing, influencing each other by modification of the environment. And that's a rather new topic within ecology. Not new in terms of it started in the 90s, but I would argue that not many people really know what to do with it. Within food web theory, they have changed it into interactions webs rather than food webs, but there's hardly any good theory for it. So there's lots of interesting things going on there. So I will talk about forms of competition and also about models for competition and how they have developed through time. And this is the one that I skipped in my mind. So this is the classic example of an organism that modifies its environment. This is the beaver. The beaver makes a big dam and that changed the whole landscape behind it. The classic example from the 90s of the organism that does what's called ecosystem engineering. That's a term that's labeled by ecologists. Will you not start talking about my lecture of tomorrow? So you're very much right. You're very much right. I will talk about that tomorrow and how that creates actually spatially structured ecosystems. Yeah, yeah. That's absolutely, yeah. Okay. And so types of competition. You have, of course, resource competition is a classic example of how organisms can compete. But you have what I call bioengineering or ecosystem engineering competition. The terms are a bit variable sometimes. And so what the difference is, if you look at ecosystems that are governed by resource competition, they often have many species. Landscapes that are governed by engineering competition don't have many species. Species don't want a mix. They spread out in different patches. And one patch is like this, the other patch is different. And that's a thing that will look further in more detail. So first, I want to, as I'm always interested in history, I want to go back to the basics and look at the classic model of competition. And this is the Lotka-Volterra, again, these guys, resource competition. And basically what they did is they had this logistic growth equation, and they said like, well, you know, in the original one, now it's time to get to the board again. So, I'm just copying what's up there. So this would be a model of only species 1 competing with itself. You have a growth rate R. If there would be no competition, it would be exponential growth. If it competes with itself, you would have a term here which says like, well, the growth rate decreases if you have the N increasing population size of species 1. It reaches 0 when N1 is equal to K1. Then the population dynamics is 0. But you want the other species also in. So what is the most simple thing to do? Is to just add them in the same way. So you say like, well, there's N2 divided by, I always forget which one this. So, of course, if you make it like this, then you are making the claim that the effect of species 1 on itself is exactly the same as the effect of species 2 on species 1. And that's not necessarily the case. It can be different. It can be a stronger competitor or a weaker competitor. And then what you do is you put a parameter in front of it, often alpha 1, 2. But it's just a parameter that translates the effect of species 2 on species 1. And so this is basically the idea behind the Lotka-Volterra competition model. And if you want to analyze this, you can do it in the same way as we did with that model. You can, again, you have two orderly differential equations. You can do a phase plane. So we can draw it here. And here we have N1, here we have N2. And we can put this to 0. And then you can already see, you can remove many of the ends. Well, anyway, it comes down to, I'm not going to make a derivation here. It takes too much time for me. And so basically, if you put this equation into a line, then it comes down to a line that looks like this. This is only the effect, the growth rate of species 1. And so one thing is important to realize. If there wouldn't be any species 2, where would the equilibrium of species 1 be? Where's an idea? Anybody? Of course, if you don't have any species 2, that one is 0. And the isocline for this curve, meaning where the growth rate is 0, would be basically hitting the N1 axis here. So the equilibrium for the species in isolation sits here. And so, of course, what we did in the former thing is that we dissected the whole region into two parts. And we said, like, well, in one part, the population, I mean, this line separates the area of positive growth with the area of negative growth. So one part must be positive, the other part must be negative. So if you're here, is the growth positive or negative? Negative, he says. Anybody who says it's positive, you have to have some nerve. Huh? You think it's positive. That guy has some nerve. Of course, here, there's just an overwhelming amount of N2. And so N1 suffers from a lot of competition. So N1 goes down. And here, there's hardly any competition, not from itself, not from the other guy. So it goes up. And this is with one of the species. If you now have another species, and this equilibrium is here. And then we have here the equilibrium for the species in isolation, and it's alone. And the other species is 0. And we have, of course, two surfaces again. And we want to know whether N1 or when N2 goes up and goes down. Well, the story is just the same. The curve is not principally different. Meaning, up here, population goes down. Up here, population goes up. And up here, you can already see, basically, this one goes up, and this one goes down. Becomes really small. And here's the other way around. So this one goes down. No, this one goes down. This one goes up. Of course, these are two straight lines. And you can configure them in different ways. You can put them like this, but you can also change the angle, and the configuration can be different. They actually don't have to intersect at all. They can also not intersect. If they are parallel to each other, they won't intersect. So I'm going to do a little quiz. I like quizzes. So this is what I just explained. And here we are again in my simulation. So this is the same setup as formerly. And you guys have to guess where we end up. So here we have the Lotka-Volterra predator-prey model, and we start at a very low prey, very low competition model. We start with very low species 1, very low species 2, and we will end up at one equilibrium. Who has an idea which equilibrium we will go to? Who is in favor of the blue dot? Blue dot, blue dot, blue dot. So the others are all in favor of the green dot? So who is in favor, the red dot. Who is in favor of the red dot? Oh, it's about 50-50, and there's a lot of people who are sort of indecisive. So we'll see where we end up, and then we try to explain it. First goes up, and we cross the line, and we end up with the blue one. Yay! So why is that? Who can say in one sentence why the blue one is the winner here? One sentence. Nobody? Come on, guys. You're a physicist, and you're not able to answer an ecologist? That's impossible. That's not great.
It seems that species 1 tolerates the same conditions better. It's just better.
What conditions? They're just competing with each other. It's like fighting.
The presence of, yeah, I mean, in this scenario, it's just, it takes...
Well,
it takes longer for it to stall, right? It basically is just doing better than the species 2, essentially.
And why?
It stalls at a higher population, essentially, right?
Okay. Well, if you look at the graphs, you can see the red one is underneath the blue one, meaning that the blue one can still grow, have positive growth, when it's on the red line. And you can see it, the blue one actually, you see as it crosses the red line, it goes horizontal. So it goes that way. It's because at that moment, the species 2 cannot grow anymore because you're at the isocline, but blue one can still grow. So you end up with a system with only the blue one, species 1. And so, given that situation, if we have this one, or actually I thought I had one in between, but this is a different configuration. Of course you understand, I was actually expecting, if we just switch this around, then it goes to the other equilibrium. The one that's on top wins. It's a simple rule, isn't it? If you're on top, you win. You can remember that, even as a physicist. So that's. I will keep on making physicist and ecologist jokes. Anyway, and now. Anybody? So we have 3 equilibria here. And the middle one, that fact is open, doesn't mean anything. You have 3 equilibria. You have the cross-section in the middle. That's a possible outcome, because both are 0 there. You have the blue one and the red one, which in isolation, they are in equilibrium, but you don't know what happens there. And of course, 0, 0 is in equilibrium, but that's a bit trivial. So, who is in favoring? Well, there's 3 options. There is red, there is blue, and there is the middle. Who is in favor of red? 1 red, 2 red, great. Who is in favor of blue? Good question, good question. Good question. We're not going to translate that. This situation doesn't exist in the United States. That's my little guess that I will sort of... And so, who is in favor of the middle one? Most of the people favor the middle one. So let's see. It looks like the ones favoring the middle are right. So if you think about this idea, the top one wins. And you go to these equilibria. The blue one, you see, is underneath the red one. So the top one wins. Red can grow there, blue can't grow anymore. On the other side of the spectrum, of the plot, the red dot, the red equilibrium, the blue one can still grow. It has no problem there. The red one is stuck, the blue one can still grow. So you can see that these will not be equilibria. Only the middle one is in equilibrium. And I think, I'm actually not sure what sort of things I have to the left. Yeah, it doesn't show. Do I have another one? So this is basically just your question. What if you have... Oh, sorry, this is a different one. If you start at a different position, you will always end up in the central point. Always as focuses. Competition will get you to the middle ground. This is the European configuration. Now we're going to the American configuration. It's following your joke. Which is, oh, sorry, I go too fast. So, what you now see is that the blue one there is over the red one in that corner. So the blue one is okay. On the other side is the red one. That's okay. So what happens now? Who votes for red? There's no Republicans here. That's good to see. Or I shouldn't say that. It's a political statement. Be careful here. Be careful here. Then there is the blue dot, which is over the red dot. So who is in favor of the blue dot? Who is in favor of the middle dot? You have good hopes, yeah. Won't work. Let me show you. So you can see here, the blue one wins, because both can survive in their own equilibrium and kick out the other one. But with this simulation, you end up in that section. Of course, that depends. You can already see that, well, if both are stable, there must be a sort of border in between where depends on where you go to. And that's, of course, well, if you start just a little higher, the begin point just a little higher, then the red one wins. So will you ever go to the midpoint here? He says no. Who says yes? Who thinks, okay, you can reach the midpoint? There's 2 who think that you can reach the midpoint. Well, you can have a look here. We start here. And then we go. You're right or not? of course, there's a boundary. If you put it on the boundary, it moves to the center, but you can never put it perfectly on the boundary. So you go either way, on that way or that way. So this is a bit of fun with Volterra equations. Okay, so you can see that depending on the configuration, and you can actually mathematically derive that from all the parameters, you will have these three, actually four possibilities. You will have one winning always because it's on top of the other. You have the other configuration where it's the opposite. You have the European configuration where neither of them are dominant in their homogeneous equilibrium, or, well, equilibrium. So the other can invade, and you end up in the middle, and you have this situation where actually it depends on starting conditions where you end up. And you have a boundary in between, and actually that line there, this part of the dot, is sort of delineating the upper part of the separatrix, as it's called by mathematicians. Any questions about this? I have a question for you. What do you like this model? It's fun though, eh? We can play games, but so what are they competing for? Not defined. They're just influencing each other. There was, of course, a bit of a limitation of this early model, in that actually it's not really defined what they're competing for. And because you don't define that, you also don't say anything about the type of dynamics that involves. It can also be different. So, how am I in time?
50 minutes.
50? 15 minutes still. Okay, I have to hurry up a little bit. And so, yeah, I have a couple of nice stories to extend on this before I go to other types. This is a person that made a very important contribution to the world of competition. It's also a very nice story. This is Gauss, a classic name in the competition world. And it's funny thing about it is that he was a young student, 22 years old, and he applied for a position. He was a Russian, Georgy Frantsevich Gauss. Well, I probably don't pronounce it correctly. And so he wanted to go to the United States to learn about how to model this. And he went to Raymond Pearl and wanted to have an MSc fellowship. And he was turned down for the Rockefeller Foundation, as everybody applied to, because he was too old. And he should just go home and mature and do some stuff and work on competition and so on. So that's what he did. And he did classic experiments on competition with paramecium. It's a small little eukaryote, single-celled. And he basically gave a very nice empirical background, empirical basis for the competition between these two species. They compete for algae, although that was not an important part of it. But you could basically tested the Lotka-Volterra equations, and it even worked. And he published it in Science. And now this is classic work. And then he went back to the United States and asked whether you could now get a Rockefeller grant. And he didn't. They turned him down again. Sort of anti-Russian, also already in these days. There was but I think his fame went along, and he's now a very, very well-known name. I know Raymond Pearl because of he was supervisor of. I've got no idea what the man did, and so. Well, the struggle for existence comes out of there. And of course, also here, the question came up, like, what are they actually competing for? And that's an important part that I want to touch upon earlier on. So I'm going to skip this one. So this is a very phenomenological approach. It doesn't deal with what is actually the point. And so we can make different models. And this is, I could easily fill the whole afternoon with this, and I'm not going to do that. I want to just give you a taste of the essential point of that. So what if you have two species of algae, and they are competing for a resource? So you need three differential equations. And you just make it completely classic, Holling 2 functional response, or Michaelis Menten Monod, or whatever. Linear mortality, they eat the resource, which is here some nutrients. Nutrients have an input rate and an output rate. And so, of course, here this is a constant. It's sort of in a chemostat, it will be dripping in. It's the conditions which did these experiments were often chemostats. So basically basins where you have water dripping in. And if you look at this, you can, of course, do a competition model, as you can see here. And here you see that one wins and the other does not. Well, how can you explain this? Well, then you have to look at what happens if you put them in isolation. And then, well, I'm skipping ahead of myself. I'm sort of mixing up my lectures here. Anyway, so what happens here? Well, it turns out, of course, they are competing for the resource, and they're depleting the resource, and they're lowering the value, and that leads to that one of them wins and the other does not. And you can look for that value by basically just solving this equation, which basically means you have the holding two functional response, which is one part of the growth equation, and you have the mortality rate, which is the other part of the growth equation. And the point at which they are intersecting is where the population growth rate is in equilibrium. And so you have two equilibria, one for each species. And you can already imagine that if you're a red species and you are competing for the resource and you lower it to this value of R2, that's where growth stops. You cannot grow any further, but the blue one can still continue growing. And it lowers the resource below to a value that it does not cannot grow anymore. And so that means at that moment the red one is having not enough food, while the blue one can still continue and reach equilibrium R1. And this is called the R star concept, R star principle, put forward by Tillman. It's way more complex than what's put forward here, but the essence is the species, if you're competing for a resource, then for one resource, the species with the lowest equilibrium concentration will win competition. And so now it becomes more mechanistic. And you can see, if you can look at LG1, it leads to an R star of 0.5. You can look at it, the other one in a simulation, you have an R star of 0.6, and in combination as you can see here, if you start with a simulation where you favor the red one with a bit more biomass, you see that first the equilibrium concentration is lower to R2, then the blue one slowly kicks in because it started with a much lower density. It lowers the concentration to the R1, R star 1, and the blue species wins. Okay, so this is a term sort of contradicting the paradox of enrichment. How can you then explain this phenomena? And actually, I think I left this one in because I'm actually not going to continue with this. I wouldn't have time for that anyway. I want to go to the other type of competition, which was a very new one, competition for a limiting resource. And I want you to look at this little picture. This is a picture that actually shows that sort of competition happening. This is a salt marsh, and what you see is, well, what's striking here? Please tell me. Patches, strong patches. And you look at this grass, it's like full cover, huge density, and then within 10 centimeters gone. And then you have completely bare soil, sediments. And that's a whole story of it, but the chemistry of the soil is strongly influenced by the species. But a very important aspect of it, another picture, is if you have a good look at the sediment, you see it's full of little droplets, which is basically just the poo of small little animals. You see here, this is the cow of the mudflat, as I call them. This is Nereus. Look, this is a container about this width. It's full of little, you might recognize them because if you go fishing, you can buy them in a shop, and these are huge ones. These ones are basically just this size. But this is for 30 square centimeter, this size, you get so much of these worms out. If you do that per square meter, it's about 1,000 worms per square meter. And do you know what they eat? Grass, particularly the seeds, but also the seedlings. The big ones they can't touch anymore. But they can really prevent them from going into these areas. So what you see here is basically competition for, sort of, on one hand is it's predation, and it's an effect of the grazing, but another aspect is that these worms are constantly mixing the sediment and changing it and making it, and keeping it in that way lower and more wet. And what also builds up in the soil is a lot of anoxia. So if you would put your hand in the sediment, you would come out black. And so it's actually a difficult place for the plants to live in. You also have, sorry, I wanted to go back. In these patches, the plants aerate the soil. They build up the sediment. It becomes higher. It becomes better drained. There's more oxygen penetration, and therefore it's easier for these plants to grow. And so, if you make a model of this, you could make a model basically like this. You take so this is something that I just did because I thought it was a cool experiment. It's just a thought experiment for myself. It's not published. But so if you want to publish this, you can pick it up and publish it if you like to. I never did that, because I'm now into patents and not into competition. But you can just make a sort of a Lotka-Volterra competition model like this. You put S here, which is the amount of sediment height, where you sort of say like, well, one organism likes the sediment to be high, the other organism likes the sediment to be low. So they have contrasting conditions. But also, they have a different effect on these conditions, where one species has a positive effect on that sediment, and the other species has a negative effect on that sediment. And so I just want to show you some illustrating simulations to show what that actually results in. This is a picture of species 1 alone. So what you see is that if you allow the green species in, let's say it's the sediment level, yeah, that's the grass. So it builds up. The engineer 2, which is the worm, does not build up, and you get the sediment goes up, and species 1 is happy. The other option is this situation where the red species goes in. It lowers the blue line, the sediment level, sediment elevation, and it is happy. So what happens if you put them together? Well, you get this. So what you see here is that it depends on the starting conditions, of course. You get you start with a bit more of engineer 1, then both of them start increasing. But as the sediment is pushed up by species 1 and increasing to a higher level, species 2 has a difficult time and it drops down. And so this is one configuration. You can also have and so to come back to this, so what would be the difference of this type of competition with the other type of competition? So this is one format I show, and you can also start differently, and then the blue one goes down and the other species wins. What's the difference between this type of competition and this type of competition? This is competition for a resource. This is a competition for engineering effects, by means of engineering effects. What's the difference? Who sees this? I'll show you again. This one or that one? Look at the x-axis. This one or that one? Resource competition is much lower. You think about it. What if you're reducing your resource? You lower the growth rate of the one species, and you lower the growth rate of the other species. Both are lowered. And your competition goes slower and slower and slower as the resource goes down. It's not the case by engineering competition. As one is favoring itself, the other one is depressed and favoring itself even more. So it's always an amplification effect there. And this, to my opinion, explains why in these sorts of systems, you have this very contrasting landscape, because it's like it goes either way or the other way. Well, if you look at a typical species, like a meadow, which is phosphorus limited, you see loads of species, because they never can outcompete each other, because the process of competition goes so slow, and there's of course always changing conditions. Here, the effect of that is much faster, and so you get this very contrasting landscape, where actually it's dominated by 2 species. One grass species and the luckworm. Of course, there's more. But the dynamics of the landscape is dominated by 2 species. So this is what I tell my students, because I go from the classic ideas of competition. I said, like, well, there's more. I have not found any paper dealing with this so far. So if you think it's a nice topic, you can go along with it. As Veronique was saying, the whole idea of modifying the landscape has very much been taken up by the people studying pattern formation in landscapes. And I will talk about that tomorrow and show you versions of that. Any questions, Jim?
But isn't also true that you are ignoring some correlations in space as well?
Sorry?
Because you assuming that it's very well mixed, right? The two species and the competition resources in the mean.
Initially, it will be well mixed, but you see them in this ecosystem, you see them separating out. So there's definitely a spatial correlation effect, which has a sort of a minimal scale in these patches, at least for the ones that persist for longer. You can see these patches about. And so there is this is a strongly autocorrelated landscape without having a characteristic scale. Of course, here at least, of course, there are spatial interaction. You see all the creeks running, and so there is actually a lot of spatial interaction. But here, if you look from above, it looks like a rather random landscape. Meaning it basically you have these two phases, grassland phase and a lugworm phase. But it's not necessarily that leads to a regular landscape, or even that spatial interactions are really that. It looks like any random initial condition is sort of picked up and translated into this landscape.
So if you zoom out, it's like a mixed.
If you zoom out, well, if you zoom out here, then suddenly there's a dike, which actually it sounds a bit silly, but that's actually a big point. It's a very small scale landscape. The landscape shaping processes are not very strong here. If you go to the really large salt marshes, you suddenly see a very structured landscape. I will talk about that on the last day, because in that scale and with that type of intensity of water flow, you do get much more patterning, landscape patterning in form of creeks and side creeks and the whole vegetation following that creek structure, basically. That's,
okay.
Yeah.
I'm super curious because I like to hike, right, in mountains, and then you have these bog landscapes, sometimes high, which looks very similar. So don't shoot me, I know they're different species. But basically you'll have high grass and then parts of moss and high grass and parts of moss. And like, you sort of like, you know, you're sogging into the mud. Do you think it could be a similar process? Do you know what I'm talking about, this sort of boggy...
Real peatland landscapes are highly self-organized in beautiful striping patterns and so on.
Yeah.
So typically, you have to, if you want to see that, go to Siberia. Here in the Netherlands, in the Netherlands and in Europe and so on, they are so much disturbed. We have little fragments of peatlands left, and there you get indeed that random processes create pools and depressions. If they get some more time, you would see that you have trees growing on patches next to parts that are actually moss-dominated, so you get differentiation between higher plant-dominated patches and moss-dominated patches. Yeah. And so you have different scales of patterning. Our understanding of that in terms of the ecology of it, like the field work, is very much determined by the fact that the only things that we have in Western Europe at least, although actually there were very nice systems also in Brazil or in the northeastern part, about northwestern part. And if you go to the places where there is enough time and sufficient lack of humans, you can see the most beautifully patterned ecosystems, which are highly structured, not patchy at all.
So what's the length scale? So how should I envision these? I think I saw them flying over with a...
Pools of about meter, 2 meter, 3 meter scale. Okay. Then the stripes of the landscape on the scale of 25 to 50 meters.
Wow, okay.
With pools in between them, and that's typically that's the story of the Romans finding their way through the maze work and then dropping into the peat. In the Netherlands, at least, that's the story of how they never reached we get a bit of European history. The Romans were never able to reach the Frisians in the north of the Netherlands because of the peat bogs, which were just maze works. They just couldn't pass it. Well, the Dutch could, and so they used to be highly structured. But the human interference with them make them very patchy now. Yeah, they will probably develop into most beautiful landscapes. Take a few hundred years, if not thousands. It's a very slow process. Likely, we don't know, but we guess.
So grazing animals disturbs that patchiness.
You won't have any big grazing animals in that because you will find
Well,
them
you
back
have- you
out
have
of the peat
some sheep.
later.
Okay.
You have smaller mice and these sort of things, but they are too small, I think, to...
So one question: Would you imagine those systems moving
uh,
on a slower, or do you think those peat bogs are so stable that they would just be fixed?
if you get Google Earth and move the slider up and down, you don't see any change.
You don't.
If you think about the process that should generate them, they are highly striped. Any model that makes stripe is always a directional process,
Yeah,
at
yeah.
least when the stripes are really consistent.
Yeah,
So it's aligned to the water flow direction,
yeah.
giving the suggestion that it's actually that basically little dikes
I see.
of peat moving down,
Yeah.
but we don't have any evidence for that.
Very nice. Thanks.
Yeah, okay, so thank you for the lecture. I really liked it. I was curious about these chaotic dynamics that you showed, whether there are, in the three species model, right? Whether there are experimental experiments in ecology that show this chaos.
I hope I can reach it, because I just tossed it out of the lecture, thinking that it would. Well, actually, maybe the amount of stuff was just enough to make something really interesting. But I can show you a few pictures, if you like. No, I have to go to Dropbox. This school, this backup, and so this is my chaos talk, and I won't give you a whole lecture, but you know this, I guess. If not, then please study physics. Logistic map, and that's what I just showed. And then there were people showing, basically, this study, showing how biodiversity could be explained by models where actually they have multiple resources. They have a whole set of resources, but like 3, 4, 5, and then put 20 species on it. And they could have 20 species survive on this 5 resources by going into chaotic regimes. The chaotic regimes were supporting species coexistence, but only specific configurations, because the species needed to be aligned to the chaotic regime that characterized that state, and it would be flips between regimes, and that's basically that work. And then this guy came with this nice container, as I said, and which he had scooped out of the Baltic Sea and traced that, and they studied this, made all sorts of experiments, and basically showed that the dynamics of all these species followed what's called the Lyapunov, positive Lyapunov exponents. But it comes down to that you have a reducing predictability as time progresses, and that's so you can forecast things in 2 to 3 days, but not in 3 weeks. To translate that, it's about the same scale. Like this is similar to the weather. It comes down to that, and this picture made it a paper in, I think, another paper in Nature. Did I put that in? Yeah, I can see it here. And so basically, because they could show that under utterly constant conditions, and with a lot of hard work by a person that just went on for 3 years, counting all the species every day again, under constant conditions, you could show that actually the chaotic regime persisted and had all the hallmarks of chaotic dynamics. I'm not an expert on chaotic dynamics, so I hope I don't say anything wrong. But I thought it was really nice, because I saw the process of Chef, I know Chef from when I was younger, Jeff Huisman, and he got a lot of criticism. It's like, here this guy comes with all these fancy models and this chaos. Yeah, that's not real. That's not, the real world is not like this. And then this German comes with this tub, and this just shows the point. So that was a very nice story, basically. Yeah.
Going back to the previous discussion, how do you decide what scale of a pattern is of interest to the system involved?
Sorry,
So patterns occur at different scales for the same systems. And how do you decide which scale is of significance to that system?
I'm not really sure that I understand your question. Scale? I didn't. You mean spatial scale? Or you mean? Oh, it's the. So which system do you refer to?
I think this came up in general during your previous discussion with her. Yeah.
Oh. Yeah, well, we've never really tried to predict these. We just observe and we try to explain. And then you, of course, it's in Siberia. You can't parameterize your model. And so you tune your model so it fits the data. Yeah, and then you hope that, and you then start to argue for the processes, whether they are really there, whether they're measured, whether there's data supporting of the processes, which makes the case a bit stronger, but it's not a proof of the model being right. Okay. And yeah, well, actually there's beautiful Arkhangelsk. So I'm interested in coastal peatlands, and there are the most beautiful things in Arkhangelsk. But yeah, you cannot go there. I mean, there's no way. It would be so nice to go there, and that's yeah. So we do it with models. Yeah.
Right. So I think we can stop here and go to the coffee break. You can start from there. And remember that we start at 4. Okay. We'll ring the bell anyway, but.